Hello everyone, this is a presentation for CS536 final project. Our topic is ChatGPT voice assistant. Our goal is to develop a mobile app that acts like an AI voice assistant. We use ChatGPT API to generate text response. Aside from ChatGPT API, we build our own API on the server by running a local language model for comparison. In our app, we support both guest mode and user mode. In the guest mode, once the client finishes speaking, the client will send a request to the server, and the request will contain all the message so far. The server will use this message to generate a text reply and send the response back to the client side, and then client can hear the audio feedback. For user mode, the client will log into the account and he can see the previous message. And in the user mode, when client finishes speaking, the HTTP request will only contain the new prompt and the username. And the server will use the username to obtain the previous messages and use all the messages to gather text reply. Once the server gets a reply, it will send the HTTP response back to the client side. Here's the overview of our framework. We will talk each component in details later. The first is front-end. For front-end, React Native is used to develop applications for Android and iOS platform. And our app contains 3 pages: welcome, login, and home pages. In the welcome page, the client will determine which mode is used. If the user mode is chosen, it will direct to a login page where the client can fill in the username and password to log in. If the client logs in successfully, he will see home page, which you can see the picture here as a reference. In the home page, there is a microphone icon at the bottom. The client can click the button to speak. Here we use a package called React Native Voice to convert voice to text. Once we get a recognized text, we display the text on the screen and send a request to the server. Then we wait for the server's response. Once we get a response, we use React Native TTS to convert text to speech. Follow this procedure, the client can have an audio conversation with AI assistant.
For the server, we use the Fast API Python package to receive and respond to post requests from the client. In addition, we also deploy a SQLite database to store the user message history. This is to reduce unnecessary data transmission and remember message for the next login. We use 2 different AI models for the chat function, namely the OpenAI GPT 3.5 model and the Llama 2 model. Llama 2 is an open source language model released by Meta. We utilize the Llama 2 7 billion parameter chat model, which is fine-tuned from the base model for dialogue. We deployed our model both on our own computer with GPU acceleration and also on the Purdue CS servers using the Python Llama C++ package, only running on the CPU. For the experiment, we measure the network latency and the duration it takes for our server to process the client's request. In this experiment, the device is connected to the campus Wi-Fi, PAL 3.0. The experiment runs under 3 settings. The first setting generates response messages using the Llama CPP language model deployed on the Purdue server. The second setting generates responses using the official ChatGPT API through Purdue server. The third setting is the same as setting 1, but the server is deployed on the home PC. Our home PC is exposed through the internet using a tunneling service called ngrok. The exposed port is the SSH port 22, so we then use SSH tunneling to access the HTTP server hosted on port 5366 on the PC. Under setting 2, the client sends the request to Purdue server, and the server will generate the messages through ChatGPT API. The table shows the experiment result under setting 1 and 2. The difference between these two settings is the source of AI response. Processing time is higher when utilizing the local language model. This is because OpenAI has powerful computing resources such as GPUs and optimized performance through parallelism. In contrast, our computations rely solely on CPUs, resulting in poor performance in terms of handling requests. To improve the processing time, we deploy the server on our local machine at home, which is near campus, and make use of a single GPU to accelerate the computation for the language model. From table 4, we observe the processing time is reduced by a factor of 100 compared with setting 1, implying the efficacy of the usage of the GPU. However, the network latency increases a lot because the routing path is different. The increase in the network latency of this experiment is due to the extra hops created by tunneling. In this experiment, we examine the influence of user mode on network latency. We send a series of questions to the server under 2 different modes and measure the network latency. Request sizes are larger under guest mode because we need to send all previous messages to the server. The top right graph shows the latency under user mode is relatively stable, while the latency under guest increases as the number of messages grows. In this experiment, we revisit the setup of setting 1. While our first result used a 7 billion parameter model, we also compare running a 70 billion parameter model. We share the response to several short questions, where both models generally provide similar responses. We see a slightly more nuanced response with the 70 billion model with the question related to division. However, we can see that runtime significantly increases with the larger model, increasing to 132 seconds for the 70 billion model. Our analysis shows that the Purdue server is not well suited for handling large models, as it would make more sense to use a GPU accelerated server. Here is a demo of our project.
Hi, I'll now be showing you our chatbot in action, which is able to respond to questions spoken in audio and also produce audio responses. When you sign into our app, you'll see 2 options. You can either register an account or quickly talk by clicking Get Started. We're able to ask a question by clicking the microphone button shown here. Hey, what's 2 plus 2?
2 plus 2 equals 4.
We can even ask questions that build on our previous questions. Can you add 3 to the previous answer?
Certainly. Adding 3 to the previous answer of 4 gives us 7.
If we want to erase our history though, we can click Clear. Can you add 2 to the previous answer?
I'm sorry, but I don't have the ability to perform mathematical operations on previous answers. But if you tell me the previous answer, I can help you add 2 to it.
No problem. Can you write a poem about computers?
In the realm of ones and zeros they dwell. Machines of metal and circuits, oh how they tell. Tales of...
Here, the answer was long, so I clicked stop so we didn't have to hear the whole recording. You can also scroll up to see our whole chat. Now let's go back to the home screen. If we click Get Started again, we'll see the conversation is also gone. But sometimes you may want to persist your history. You can do this by registering an account and signing in. Let's make a new account. Hey, how are you doing?
Hello, I'm just a digital assistant, so I don't have feelings, but I'm here and ready to help you. How can I assist you today?
Now, let's go back. You can see that our conversation was persisted. We could even create multiple accounts. Hey. Hey, I'm Bob.
Hello, Bob. I'm here to help you with anything you need. What can I assist you with today?
But we can go back and switch to our other user at any time. You can even see that this conversation will get persisted if we restart the app. Can you write a poem about computer networking?
When the screen of blue disappears and the system's hum becomes a whir, the computer sits in.
That's great, thank you.
You're welcome. I'm glad you liked it. If you need anything else, feel free to ask.
Alright, that shows all the main features of our app. Thanks for watching. Hi.